Hi, welcome you again to the lecture 5 and this example 2. In this example, I'm going to show you two examples, and one from the Newton's gravitational law and how we can calculate the acceleration due to gravity on the surface of the earth and the same time on the surface of the moon. And we will also see that how acceleration due to gravity, that means g, varies with distance from the center of a body. Okay, in the second example, we will see uh, the mechanics problem, and that is from how we can write a code for a spring constant for constant spring speed, something like that. Okay, let's see. This is acceleration due to gravity problem, and this is the mechanics problem. So Matlab programming Fx equal to k. How we can calculate the displacement of a spring due to applied external forces, and how we can calculate the potential energy stored due to the forces and displacement, something like that, with various forces and various spring constant. Okay, this problem I've taken this problem from the Matlab programming engineers for engineers by Stephen J. Chapman, and which is published on November 8, 2007. Okay, so that first we will concentrate to the acceleration due to gravity, and we know that is the equation g equal to gm divided by r square, and this is the law or equation to calculate the acceleration due to gravity of a object. Okay, so what is the g equal to the universal gravitational constant? The value of this 6.67384 in 10 to the power minus 11, and m is the mass of that object, and r equal to the radius of that object. Okay, so we can calculate using those parameters, uh, these parameters, and we will calculate acceleration due to gravity in case of earth and in case of moon. So we have parameters here. Okay, we will also see that how g, that means how acceleration due to gravity, g varies with distance from the center of the body. That means if we reduce or if we decrease or increase the r, then how g can vary. Okay, so we'll also see that. Okay, let's go to the Matlab then. Okay, let's go to the Matlab. Okay, go to Matlab, and yeah, let's clear this. So now I'm gonna open a new script, and right. Okay, so we need a g equal to 6.672 e to the power minus 11. This is the gravitational constant. Okay, yeah. So radius of the earth, r is equal to 6378.1 e to the power radius e to the power 3 meters. Yeah, e to the power 3 is the meter. Okay, the mass of the earth is equal to, what is the mass? Mass is about 5.97 and 10 to the power 24. 5.97 e to the power 24. Okay, so we can calculate gm equal to g multiplied by me. So you know about that. Yeah, so we can calculate g equal to gm divided by re to the power square, right? So we can do that. Yeah, so I hope I didn't make any mistake, and I hope it will be working. So I can save this, for example, g. Okay, g. Okay, save this. So if you want to execute from here, then you can see. Yeah, it's about gravitational sorry, g, that means acceleration due to gravity on the surface of the earth is 9.7915, and we know it's very constant, 9.8, about that. Okay, so what we can do, and we can also say we can also find the same way to the acceleration due to gravity on the surface of the moon. Okay, let's see. Okay, so I'm gonna copy this and call in the moon. Yeah, so copy this, and this should be the M with the M. Yeah, this should be M. Moon. It should be M. Yeah. So what is the radius of moon? The radius of the moon is 1.737 10 to the power 6. 1.7, what is that? 1.7374 10 to the power 6. 1.7374 10 to the power 6. Okay. What's the mass of the moon? Mass equal to 7.36 10 to the power 20. 7.36 7.36 10 to the power 22. Here it is. So we can calculate. Okay, let's see what is the result of this. So the gm equal to g into mm, that means the mass of the moon, and g equal to gm divided by rms. Okay, so let's see. Yeah, so this is the acceleration due to gravity on the surface of the earth, and this is the acceleration due to gravity on the surface of the moon. Okay, let's see how g varies with r. That means if we increase or decrease the distance from the center of the body, then how g can vary. Okay, let's make an example in case of art. Okay, let's make an example. Okay, for this I'm gonna make this inactive. Okay, so I'm gonna give a radius from 1 to 1000 millimeter up to this. Okay, so I'm gonna make the radius. That means 1 to surface, that means 1 meter, that means from the center, approximately from the center to surface, how gravity varies with this r. Okay, so with the step is 1000, that means 1 kilometer. So we will calculate g in every 1 kilometer. So the mass is constant and g is constant. How we can do that? Okay, we can do that r. So for this we can r equal to re dot whole to the power 2. That means the every component, that means we have a huge component here, a vector, right? 1 to 6, about 6037 meters, something like that. So it is a vector. So for this case we are going to calculate the acceleration due to gravity on the surface of the earth up to 1 kilometer. So let's see. So how we can do that? So this should be the re, this should be the r, this should be the r, and put should be dot. Okay, let's this should be this something like this. Okay, I'm gonna plot here. I'm gonna make a plot function, and so let's see how r that means this should be the re. Yeah, this is the re with g. So how re and g can vary with this. Let's see. I hope I didn't make any mistake here. Okay, I'm gonna put semicolon here. So I'm gonna make you understand what this. So we are going to calculate the g with various distance. That means we put here 1 to that means from the center to the surface of the earth. So we want to see how g varies from the center up to this. We know that on the center, on the surface of the earth, it is 9.7915, right? So we want to see how g can vary with r. That means we can also calculate g at the center, from the center, and in every 1 kilometer. Okay, so let's see. I hope it will be working. Yeah, it is working here. So we can see that our graph is so our x-axis is radius. So with radius so it's almost the linear. Okay, so if we see here, if we want to make our plot in semi-log plot or something. Let's say my semi-log x, semi-log x. So re comma g. Okay, then you can see, you can visualize this in very better way. So let's see. Yeah, so you can see that here. So if you put here log, then log. See how you can vary. Yeah, so from the log paper, it is very obvious that okay, this is the x-axis. That means this is the x-axis, and this is the something like that, and this is the, what is this? So this is the x-axis. This is the radius. Okay, so from 10 squared from the center. So from the center, so in the center of the earth, it is the highest gravity, approximately 10 to the power 15, something like that. Okay, and on the surface it become reduced and it becomes 9.7, something like that, 9.8. So here approximately, yeah. So we can also see this equation for also we can also visualize this for also the moon. Okay, how the gravity of how the gravity uh, due to acceleration due to gravity on the surface of, in case for moon, also varies from center from the moon to the surface. Okay, so if we put here grid on, okay, so we can also visualize this more better. Yeah, here we can put level, x level, something, yeah, x level. In on axis is the x and this is the y, so radius of the earth. Radius of the earth in meter. Okay, so y, LABL y level, it be acceleration acceleration due to acceleration due to gravity. Okay, so let's see. So you see here, this is the radius of the earth. So from the center, it is the center approximately 0, 10, right? So from the, this is a log scale. That's why log scale. That's why it shows in terms of 10th scale. Okay, so we see that the gravity varies. Gravity varies with distance linearly, right? It's not a non-linear function. So gravity, so it's linear equation. Definitely we know G equal to Gm by R square. Though it's not, I don't know whether it's not. I think it's, I don't know. It's not a linear equation, but it varies linearly here in log scale. Okay, let's see in semi-log paper. I think it's not a linear equation. Okay, semi-log y. Let's see semi-log y. Let's see. So what do you all see? Yeah, yeah. So semi-log y. That means you see in semi-log paper, you see here it's not a linear, semi-log paper, because radius is linear scale and this is not a linear scale here. Okay, and in acceleration due to gravity is not linear, it's a semi-log. Okay, so 10 to the 5, 10 to the power 10, and 10 to the 15. So we see that here, we see there is a great turn up from 10 to the 6, from 10 to the 6 there is a huge turning point right here. So it's a non-linear equation. So we see that here g equal to gm equal to r square is that it's not linear, it's the non-linear. So from the graph it's very obvious that it's the non-linear equation. And okay, so this is the way how we can analyze, how we can calculate this way, the gravity or something like that. The same way you can also calculate in case of moon. Let's see. Okay, we can compare this. Yeah, compare this for moon. Okay, let's put here 1 up to this to 1000. That means 1 kilometer. So this is the mean. So what is the r equal to r, that means rmm, okay, rm equal to rm dot whole to the power square, and this is the r, and we have to put dot here because we have to divide every element. Okay, so uh, we can put these options here so that we can put both plot. So let's see, it's a gm, the gmon, okay, and the ge. Okay, so this should be the ge, and make a dash. Okay, and this graph will be represented by the dash, and uh, rm rm by gm, and this should be represented by dot. It should be represented by dot. Okay, so let's see, is there any I hope I didn't make any mistake. Yeah, you see the both plots are here. So we can also plot, we plotted this both function here. So I had another function, I made it. Yeah, so we have got these two plots here. Okay, so if we look closer, well, then you can also see that here it is almost coincide in some places, and you also see this is also. I think I didn't make any mistake. Yeah, I had another function gravity here. Let's see. Yeah, this is the original function. This is the GE equal to RE, GM, RM. So this is the acceleration due to gravity in case of the Earth. Okay, I had another code I wrote. I have written previous than this. Okay, so this is the acceleration due to gravity in for the Earth, and acceleration due to gravity for the uh, moon, and I put the semilog x, and we wanted the gravity value should be should have a 10th semilog log paper. Okay, okay, so this is the way how we can do that, and how we can analyze our computational physics, chemistry, and mathematics, whatever we want, and we can analyze our functions, analyze our mm, data easily. Okay, so let's make one thing so that we can do another interesting thing. Let's assume our body in the universe which have a infinite mass, that means constant mass, but has a huge radius, something like this, or have a for different object for having the same radius. Okay, so also we can do some another example. For example, same radius but have different, same radius but different mass. Okay, so the different objects. For example, you can also assume that there are the different bodies here in the universe, different same size bodies with different mass, that means different density. Okay, so we can also calculate g with various m's. How we can do that? Okay, let's put the same radius here, same size. Okay, so mass should be varied. For example, 1 to 1 10,000, something like this. Okay, mass should be varied here. Okay, so let's put here 2007. Okay, so how this can be varied? me dot multiplied with g, so this should be gm. Okay, so equal to rds square. So Let's see. I don't know whether it will be working or not, but let's see. Inactive, inactive, yeah. So, oh, this shouldn't be, yeah. What is that? Terminate to fix. Yeah, okay. I didn't put semicolon here, so r equal to r is square. So gm or something. Let's see. I think I've got a mistake here. So m equal to 1000. 1 up to 10,000. I think 5.97 to the power 27 math. Let's see. I've gotten the mistake. What is that? I don't know. Okay, let's into 1000 up to 1. Okay, let's see how bad it is. And I've got the same mistake here. Vector must be the same length, and okay. R E, where are, oh no, this should be the M E. Yeah, M E. So how it varies? There is no data. That is the mass. This should be the mass of the Earth. This X level should be the mass of objects. Mass of objects, and acceleration due to gravity in the y-axis. Okay, so let's see. Any graph here? No, I didn't find any graph here, and okay, this put here into 1 divided by r, right? Yeah, so I hope this time it will be working. 1 divided by r. Yeah, I hope so. Let's see. No, I didn't see any graph here, so I think I'm going. Okay, so this is the way we can do that, and okay, I'm gonna fix this here. Welcome back. I hope I have fixed the problem, and what it was. It is very interesting for us that, and that is the ME, and we have put that is a huge data, right? 1 up to step 1, 2, 3, 4, 5, 6, 7, 10 to the 7 up to this. So there is a huge data. So if you want to execute this, so what it will say to us? It says here the maximum variable size allowed by the program is exceeded. So we are not. So if we execute, or if we want to execute this, so we will not get a result because the maximum variable selected by the program is exceeded by. So we have our memory shortage and we have our program shortage. That's why we cannot do that. So what we have to do, we have to reduce the size of this. Okay, let's make it 15. Let's see whether it does. Okay, there is another option. If we want to put uh, put here, then you will see that there is a black circle, right? Okay, so if you want to execute this pressing F11 step by step, then it will So it will stop here, so it will not execute from here. Okay, so if you press F11, then you will you can go from line by line again. So this is also the same problem here, line at ME, so we have to reduce this volume as well. Okay, let's make it here 10. I hope it will be working right now. Okay, so if we want to press F11, yeah, it does work right now. Okay, there is another option. There is the workspace. So from we can get it from workspace, and we can get all the data we are going to calculate here. So at first we added a variable d. So there is a variable d here. It added here. So m radius re. So radius re is added here. Okay, and the ME, which is a vector, and there is a series of data here. So the ME is added here. So ME equal to, so minimum 1. So here our minimum 1, and the maximum equal to 5.96 10 to the power 10. And here, so he's database. So if you want to see what are the data here, so you will see this is the data here. So you have a huge amount of data. So how many data are here? There are 5,970 data variable here. So again, these are the mass. This is the mass of that object. Okay, with constant radius. Something, yeah, it is. Okay. So from workspace, you can take it from the desktop workspace. Yeah. So now go back to our program. Okay. So press F. So we'll get the series of data as well of GM here. So press F11, G11. So we have got GM. GM will get also the series of data, minimum this and maximum this. We're going to calculate the, yeah, we have succeeded GE. So we have got the GE. So GE is to calculate the GE for the data of ME. So let's plot this data in semilog F. Yeah, so press F11. Yeah, we have got the data, and press 11. Press 11, or you can press it here to continue. Okay, so we have got our plot here. So this is the mass of objects. That means from 0 to 10 to the power 10 up to this, and we have for this mass we have calculated the acceleration due to gravity, where our radius is fixed. Okay, radius is fixed. That means at first we have calculated for 1 meter object, 1 kg object having radius 6,378 meter into 10 to the power 3 meter. So it is very low density, low dense. So what is the acceleration due to gravity of that object on that object surface? It's about 10 to the power 24. It's very low. But it is obvious, it is very clear that having the acceleration due to gravity also depends upon the density of this object also the same way, and radius or the distance from the center of that object. Okay, so in case, so if you see the last value here, our what is our the last 5.97 is about the same mass of the earth. No, same mass of, no, it's not same mass of the earth. Same mass of that is, it should be the 24. Okay, so an object having the mass 5.97 10 to the power 10 kg and the constant radius 6, same radius, then what is the gravity? So acceleration gravity is about something like that. So what is this? This is about something, yeah, 10 to the power, probably 10 to the power 13 something, 10 to the power minus 13 meter per second square acceleration due to gravity. Okay, so this is the way how we can do and how we can calculate various equations, how we can compute various equations, how we can evaluate various equations in, say, Matlab. So thank you very much, and I'm gonna show you the next example from the mechanics. Yeah. and it is spring constant. Yeah, so you have completed this example. So we are going to the next example, this problem, and I've got this problem from this book, Matlab Programming for Engineers by Stephen J. Camp and Chico. Okay. So we know the spring constant F equal to kx. What this is the spring constant, and this is the displacement. Uh, uh, Displacement happened due to the force applied by this F. Okay, k is constant, spring constant, so it depends upon the type of material here. So if we are given a different spring constant here, that means this is the one material spring, this is the one material spring, one material spring, one material spring. So if we want to apply different force to that, what would be the displacement for different constant? Okay, so we can calculate this. So I have made a program for this before for you, so that I can easily um, do that. So let's open this program. Where is that? Desktop now. Example. Yeah, SPP string constant. Okay. I've made a vector of k. That means we have here. Um, what is that? Yeah. This is and okay. So we are given some force k. Now we are different k. So I've made a vectors different k. Yes. Okay. And force 20, 24, 22, 20. So I'm also made a force here, force vector. So if we calculate this, that means the x displacement, that means the f equal to kx. So x equal to f divided by k. So f divided by k. Okay. So here displacement and the potential energy half the kx square, half into k x square. So dot yeah, half is the kx square. Okay, let's execute this. I'm sure that I didn't make any mistake here. Yeah, I didn't make any mistake here. So this is the displacement here. Okay, for different materials having the spring constant 500, we put the force 20 Newton. So here the displacement is at. Okay, yeah. So we can evaluate this. So we can also evaluate same same spring with different forces. Then what will be happening? Okay, let's see. Same spring, that means same material spring with different forces. 20, say for example 22. So 22 is the 24 and 26. Okay, then let's see what happens. Yeah. So you see here is the approximately with different materials. Which material the displacement occurred mostly? The displacement occurred mostly having the evaporate force, mass force. Yeah, more the forces, and we'll get the more the displacement here, and more the energy stored in the spring here. Okay. So this is the way how we can do that and how we can analyze this, and I hope you have understood. And I'm sorry that I made some mistake on my examples here, and I have to fix that up. I'm sorry for that. Okay, thank you very much for being with us. I hope I'm gonna see you on next tutorial or next video, which is about the branching, which is about the if else statement. Okay, thank you very much for being with us.